Hi goers, welcome to the Chapter 6 review video. Today we're going to talk about alkene reactions. There's going to be 10 of them, and this is going to be the first half of the material that is covered on Exam 3, and there's going to be a subsequent video covering the Chapter 7 material, and that's going to be the second half of Exam 3. So let's just jump right in. So the first topic in this chapter is alkene stability. So when determining, the stability of alkenes, we just use the general rule of the more substituted that pi bond is, or the more carbon chains that are attached to that pi bond, the more stable that molecule is going to be. Meaning, a tetra-substituted alkene would be greater than a tri-substituted alkene, which is greater than a di-substituted alkene, which is greater than a mono-substituted alkene. So, maybe it's a good rule of thumb for you to, classify the types of alkenes in the starting material, and then that might help you, rank the relative stability of these alkenes. So let's just start with that. So if we look at this first molecule over here, we see that we have one carbon group directly attached to that alkene, so we can classify this as a mono-substituted alkene. So I'll just write mono. If we move over here, we see that we have one carbon chain attached and we have another carbon chain attached, so that would be a di-substituted alkene. If we keep going, we see that we have three carbon chains attached, so this would be a tri-substituted alkene. And finally, we see over here we have four carbon chains attached, so that would be a tetra-substituted alkene. So, our general rule of thumb was that the more substituted, the more carbon chains that are attached to that double bond, the more stable that it's going to be. So, if we said that 4 would be, the most stable, or is most stable, we can rank these and say that that's 4, that's 3, that's 2, and that's 1. Okay? So the more substitution that there is around a double bond, the more stable that molecule will be. Okay? Let's move on to another example. So let's rank these again, or let's first classify the substitution around that double bond. So the first example, we have a di-substituted alkene. The second example, we have a di-substituted alkene. And I can just circle the groups. And again, we have a di-substituted alkene. And it looks like over here we have a tetra-substituted alkene. Or tri-substituted alkene. Okay? So clearly we have three di-substituted alkenes, to rank here, and there must be another, feature about alkenes that is going to contribute to their overall stability. So if we look at our first example, or the first di-substituted alkene, we see that the arrangement of the carbon chains around the double bond are in a trans fashion, meaning that those carbon chains are as far away as possible from one another. So, we can see that the methyl group to the left is down, while the ethyl group is up. So that is completely anticoplanar, or 180 degrees apart, and that's the most stable because there is the smallest amount of steric hindrance. So when we're considering, di-substituted alkenes, we have to consider the steric hindrance that's possible. So in a trans configuration, so let's just write trans over here, we are the most stable because we have that 180 degree, lack of steric hindrance that's going on. Okay? So, a di-substituted for the next molecule, where the two carbon chains are coming off of the same carbon, gets the special term geminal. Okay, so geminal alkenes have carbon chains coming off of just one carbon of that pi bond. And these are relatively stable. They're not as stable as trans, but they're still relatively stable because, we see that we're locked in that 120 degree planar orientation, where those two methyl groups are kind of, as far away as possible in terms of being attached to that carbon. So, they're not the most stable because they're not 180 degrees apart, but they're kind of locked in that configuration where they are relatively further apart from each other. Okay, so for the next one, we see that we have these two carbon chains that are on the same face of that pi bond. So this gets the term a cis di-substituted alkene. And cis alkenes are the absolute worst because what happens is that this methyl group over here and this methyl group over here have some steric hindrance. They are relatively close to one another, so there's overlap, and that is not favorable in terms of organic chemistry. Whenever we have steric hindrance, it's not favorable. So, in terms of thinking about di-substituted alkenes, we can rationalize that trans alkenes are greater than geminal alkenes, which are greater than cis alkenes. Okay, so finally, we just have that tri-substitute. We said that the more substituted something is, the more stable it is. So we can rationalize that if we go with 4 being the most stable, our tri-substituted alkene would be the most stable, followed by our trans di-substituted alkene, followed by our geminal di-substituted alkene, and finally the worst one, the cis di-substituted alkene. All right, so I hope that helps with, rationalizing alkene stability. Just go with the rule of thumb that the more substitution that there is around that pi bond, the more stable it is. But if it's a disubstitute alkene, we have to consider steric factors. So trans would be greater than a geminal, and a geminal would be greater than a cis. Okay? So the next topic is carbocation stability. So, not all reactions like we've seen so far in chapter 6 go through a carbocation intermediate, but a lot of them do. So there's, I guess, a point to talk about where the carbocation stability, or the stability of that intermediate, is going to dramatically affect the reactivity of a molecule. So I guess you can say the more stable that carbocation is, the faster the rate of the reaction is, okay? So let's think about it like this. If you could form a more stable intermediate, then that means the activation energy is relatively lower. That kind of hump that you see on a reaction coordinate diagram is relatively small. If you're synthesizing a unstable carbocation intermediate, the activation energy to do so is very, very high because it's an unfavorable reaction. So that hump is a lot larger. So that means the reaction takes longer, okay? So let's just look at these carbocations, and let's first classify them, and then we can talk about some stabilizing features. So if we look over here, it looks like we have a primary benzylic. So a primary benzylic. Over here, it looks like we just have a plain secondary. Over here, it looks like we have secondary, but we're also close to a ketone. So we're going to have to talk about that in a second. So let's just write secondary with a ketone nearby. And over here, it looks like we have secondary, but there's something with that pi bond that's possible, and this is a secondary with resonance. Okay. So, we say that the more substituted a carbocation is, the more stable it is. So recall that, let's just say I had a tri-substituted carbocation. Remember that carbocations are electron deficient. So adjacent alkyl groups over here, so we have this CH3 up top here, we have a CH3 over here, and a CH3 over here, can actually partially donate their electron density into that carbocation to partially stabilize it. And that feature is called HyperConjugation. Okay, so we can rationalize that if we have a carbocation, and the more substitution, or the more alkyl chains that are in close proximity to that carbocation, the higher probability that some of that electron density is going to actually lean into that empty unhybridized p orbital and stabilize it. So recall, carbocations are sp2 hybrids, where we have an unhybridized p orbital, and those adjacent alkyl groups can actually slightly lean into that unhybridized p orbital and stabilize it. So because tertiary carbocations have more alkyl groups nearby, the odds of hyperconjugation stabilizing that carbocation would be a lot higher than a or a secondary carbocation or a primary carbocation. So the first feature would just be hyperconjugation. And that leads us to the conclusion that a tertiary is greater than a secondary, which is greater than a primary carbocation. Okay? So the next feature, like we've seen so far, is resonance. Resonance stabilizes carbocations because we're able to delocalize, that positive charge over a broader region. So, having a formal charge is not favorable, period. But if we can move that formal charge over a greater region in a molecule via resonance, then that's a stabilizing feature. So, let's just look at that primary benzylic. We can actually, resonate a pi bond over here. So let me just draw the alternate structure. And now we just generated a secondary allylic carbocation. So you can see that, by delocalizing that carbocation, we're spreading that unfavorable positive formal charge over a larger region, which stabilizes the overall molecule. So resonance is definitely a stabilizing feature. And let's go back to that ketone example. So when we have ketones or other, electronegative groups nearby, that's going to be the inductive effect. So we can just write induction. And induction is not favorable in carbocation stability because you can rationalize that there's a dipole towards that ketone, and that dipole is going to pull electron density away from an already electron deficient center. So remember, carbocations are electron deficient. They only have 6 valence nearby. So by introducing electronegative groups, we're actually pulling even more electron density away from that electron deficient center. So induction is not favorable even though, remember, with acid-base chemistry, induction was favorable because we were delocalizing that negative charge. In this case, we're dealing with a positive charge, so induction is definitely not favorable. Okay, so with all that in mind, let's just rank these carbocations. So we know that the secondary with the ketone, because of the inductive effect, is immediately going to be the worst. So we can say that this would be number 1, okay? Because that secondary carbocation is even further destabilized because of that ketone nearby. Then we have to look at the possible resonance structures, okay? So clearly, we have a primary benzylic over here, and we have just a plain secondary allylic over here. So those can resonate. So those should be our two relatively most stable ones. And then we just have a plain secondary here that can't participate in resonance because these pi bonds are too far away. So resonance is not possible. So this would definitely be number 2, okay? Because it's just a plain secondary. It's stabilized via hyperconjugation slightly, but it's not as stable as resonance would be, okay? So if we were to consider, the other two structures, maybe it would help to draw the alternate resonance structures to kind of rationalize or get a better picture of carbocation stability. Okay, so if we were to resonate these pi bonds up, the alternate structure would look something like this. And you can do that again, and you would get something like this. Okay, so in each one of those resonance structures, or each one of those contributing structures, you get a secondary carbocation no matter what. So the overall resonance hybrid is going to tell me that our average, or a weighted average of all of these three structures is going to be overwhelmingly a secondary carbocation. So pretty good. All right, so then if I were to look at the primary benzylic, and we were to show alternate resonance structures, we already showed one of them, and we can keep going around the ring. There's another one as well. And there also is one more. Okay, so you can see that if we were to classify all these, we had primary, secondary, secondary, secondary again, and then primary. So if we were to weight those averages of primary plus secondary plus secondary plus secondary plus primary, it's not going to be an average of secondary like we saw with the structure over here. So, when we were to average all these together, we don't really have secondary. You can say maybe something like 1.8 or 1.7, So the primary benzylic is not as stable as the just secondary allylic one all the way to the right. So we would say that this would be 3, and this one would be 4. Okay, so sometimes drawing out all the resonance structures gives us a better picture of the overall resonance hybrid and the true stability of that molecule. Okay, so that pretty much sums up carbocation stability. So now we're going to talk about carbocation rearrangements. So let me make some more room over here. Okay. So I know we haven't talked about any reactions yet, but our first reaction that we learned in this chapter is called hydrohalogenation. And through that mechanism, we saw that we're going to generate a carbocation. And generation of carbocation follows Markovnikovs Rule. So Markovnikov says, over here, Markovnikovs Rule. Says that when we are subjecting, a molecule to, some sort of reagent that's going to go through a carbocation intermediate, the carbocation is going to form on the more substituted side, and a hydrogen, by effect, is going to add onto the less substituted side of the alkene. So carbocation more substituted side, and then the hydrogen adds to the less substituted side. Okay, so that's Markovnikovs Rule. So let's just imagine that we're subjecting all of these molecules, A through F, with a hydrogen halide, like HBr. Okay, so what happens, remember, we'll see the mechanism in a second, is that the hydrogen is going to add to the less substituted side, so something over here, and we're going to generate a carbocation on the more substituted side. So, we can keep doing that. So we'll say that the hydrogen over here and a carbocation over here, a hydrogen over here and a carbocation over here, a hydrogen over here, followed by a carbocation over here, hydrogen over here with a carbocation over here, a hydrogen over here with a carbocation over here. Okay, so once we form these carbocations, they're actually susceptible to rearrangements to form an even more stable carbocation. And the driving force is actually the fact that the more stable carbocation is more stable. Okay, so we have an overall decrease in energy or Gibbs free energy as a result of forming a more stable carbocation. So, what are the possible carbocation rearrangements that we see? Well, there are three of them. So the first one would be something called a 1,2 hydride shift. And it's called a 1,2 because you're only moving a hydride or a hydrogen from one carbon to the second carbon over, meaning it's only possible via adjacent transfers. So 1,2. The other one could be a 1,2 methyl shift. Okay, so 1,2 methyl shift happens when there's no hydrogens possible to move, and the only other option would be to move a methyl group to form a more stable carbocation. When we have this choice of choosing either a hydride shift or a methyl shift, it's always easier to move a hydride than a methyl because the hydride is a single atom, while a methyl is a complete bulky group. It's a CH3 group. Okay, and then the last one would be only applies to rings, and it's called a ring expansion. And ring expansions only occur when we have a vinyl substituent, meaning a double bond directly attached to a cyclic structure, and we have the potential to alleviate some ring strain from either going from a 4-carbon ring to a 5-carbon ring, or a 5-carbon ring to a 6-membered ring. So it's pretty specific in either a 4-carbon ring to a 5-carbon ring, or a 5-carbon ring to a 6-carbon ring. Okay, so why do we do ring expansions? Well, ring expansions, recall we said that sp3 hybridized centers like to have 109.5 bond angles, and in cyclic structures we deviate significantly from those 109.5 bond angles, especially in something like cyclobutane over here, so where those bond angles are 90 degrees. So by doing this ring expansion or making a 5-membered ring from a 4-membered ring, we actually increase those bond angles, effectively decreasing that ring strain, making a more stable molecule, which decreases Gibbs free energy, and that's favorable. Okay, so let's talk about the possible ring expansions in A through F, and we can even see if any of them even go through ring expansions in the first place. Okay, so let me make some more room over here. Okay, so let's follow Markovnikovs rule for all of these. Let's imagine that we're suscepting them to hydrogen halides. So over here, we're going to imagine that the carbocation is going to form on the secondary position. Okay, so let's get rid of that pi bond over here. So are there any groups next door that we can move either a hydrogen or a methyl to make this carbocation more stable? Well, towards the right, we do have hydrogens here, but by moving a hydrogen over here, we would form a primary carbocation, and that's worse than what we had before. So we're definitely not going to go to the right. But over to the left, we have a hydrogen over here, which we can move to the right, but in doing so, you only form a secondary carbocation. So that's not really favorable. Each step, or each step in a mechanism, has to be more and more favorable, or you have to lower each time the Gibbs free energy. Otherwise, it's not going to happen. So going from a secondary to a secondary, there's no reason to do that. You're already at that stable position. So this I guess in structure A is not going to go through a carbocation rearrangement because we're already in that secondary orientation. Okay, so let's look at B. So for B, we have a choice. We can either put the carbocation on the secondary position over here, or we can put the secondary on the carbocation. I'm sorry, we can put the secondary carbocation on the position onto the left. And they both are secondary, but there's a reason why the structure on the left is better. So if I were to get rid of that pi bond, the reason why the structure on the left is better is because we can do a hydride shift to make this a tertiary carbocation. So, if I were to show the other structure over here, we put a hydrogen over here, and we effectively moved that carbocation to the tertiary position. So going from secondary to tertiary is definitely more stable because we said hyperconjugation is a stabilizing feature. So molecule B is definitely going to go through a hydride shift rearrangement. So we can just write hydride, and I can put a check mark. So B is definitely going to do a hydride shift. So, we could have put, that carbocation in either of those positions, like either the secondary position to the left or the secondary position to the right, but we're choosing the secondary to the left because we're able to do a rearrangement. On the right, we were not able to do so. Let's look at C. So C, again, we have a secondary possible over here, or a secondary possible over here. But by moving a hydrogen over here, we're going to make that even worse or more unstable because we would form a primary carbocation. So, we can rationalize that carbocation would not be the best one. But to the left, we see that we can move a methyl group to the left, And that structure would look something like this. So maybe if I highlighted over here, that structure, that methyl group became that methyl group over there. We just shifted it 1, 2 over, okay? So the difference here now is that we didn't have any hydrogens over here. There were no hydrogens to move over, so we had no choice, and we had to move a methyl. So we can say that we went from a secondary to a tertiary, and that is definitely stable, okay? So this would be a methyl rearrangement. Okay. So let's look at D. So for D, it looks like we have a 4-membered ring, so cyclobutane, so I'm thinking ring expansion, but do I have that geminal substituent that vinyl substituent rather, I think I said geminal earlier, it should have been vinyl. Do we have that vinyl substituent that's directly attached to the ring to, do a ring expansion? So basically what happens is we have this primary carbocation over here, or the secondary carbocation. So it definitely makes sense to form the secondary carbocation. And what happens is that this carbon-carbon bond in the ring, so this carbon-carbon bond, is actually going to break off and form a 5-membered ring. So let's number that over here. We can say that this is 1, 2, 3, 4, 5, 6. So if I were to draw the 5-membered ring that resulted from that, this was 1, this was 2, this was 3, this was 4, this was 5. And this was 6. Okay? So what happened is that you can see that there's a new carbon-carbon bond between 6 and 2. So 6 over here, let me just change colors. 6 and 2 became 6 and 2 over here. So you can see that new carbon-carbon bond over here. Okay? So, oops, I may have numbered it backwards. So this could have been 3, 4, 5. Maybe that helps. So at position 3, you saw that we broke that carbon bond. So we formed a carbocation on position 3. 4 we didn't touch, 5 we didn't touch. So, this is, let me just maybe fix this over here. 3, 4, 5. Okay? So if we numbered that ring like this, we saw that we broke a carbon-carbon bond between 3 and 6. So that means that 3 is now electron deficient. But 6 came and attacked 2. So that's the new 6-2 carbon bond over there. Okay? So the reason that we can do this rearrangement is because we have this vinyl substituent, and that allows us to do a ring expansion. So from a 4-member ring to a 5-member ring, we're leaving some of that ring strain. So this is definitely going to be a ring expansion. Okay? But there's something else that you can note. Once you do that ring expansion, so let me kind of erase some of this extra stuff over here. What you can do is a subsequent hydride shift to make an even more stable molecule. So now we have a tertiary carbocation on a 5-membered ring, okay? So that definitely beats just a plain secondary carbocation that's a substituent on a 4-membered ring, because now we have a 5-membered ring with a tertiary carbocation. So, this is definitely a very good problem to do. No. Okay, so for E, it looks like we have a 5-membered ring in that vinyl substituent again. So we're going to form a carbocation here. This carbon-carbon bond is going to break and attack there. So I can rationalize that we are going to form this structure. And again, you can do a subsequent hydride shift to form that tertiary carbocation. Okay? So you can do subsequent shifts as long as each time you do a shift, it is more and more stable. Okay? So for F, we have a choice of either this secondary or this secondary. And, there's a reason I'm going to pick the one on the left, and that's because it can undergo a hydride shift. So if we imagine that there's a hydrogen here, we can shift that over to form this structure. So we just formed a tri-substitute from a tertiary carbocation from the secondary carbocation. So we definitely increased stability. So this was a hydride shift. Okay? So, if we rationalize all of these went through rearrangements except for A. So the first two, B and C, went through hydride and methyl shifts respectively, and then D and E went through ring expansions because of that vinyl substituent. Okay, so I think that kind of sums up kind of the basics of Chapter 6, which was alkane stability, carbocation stability, and carbocation rearrangements. So now let's move on to the different reactions that we see in Chapter 6. Okay, so first, I'm going to draw the mechanism for all of these, and hopefully that rationalizes the products, and then I'll talk about key mechanistic steps that apply for each reaction, okay? So, when we have this pi bond subjected to a hydrogen halide over here, we can rationalize that there is a huge dipole moment in favor of that halide. So that means that there's a partial negative charge on that bromine and a partial positive charge on that hydrogen. Remember, hydrogen's all the way to the left on the periodic table and bromine's all the way to the right on the periodic table. So, that's a huge difference in electronegativity. So that means that, we have an electron deficient hydrogen towards the left, or partially deficient. And remember that pi bonds are nucleophilic because we have this huge source of electron density around that carbon bond. So imagine that we have four valence electrons right there that are able to, attack that electron deficient hydrogen. So in terms of mechanism, it makes sense that the pi bond is going to grab the hydrogen, and then that sigma bond density between the hydrogen and the bromine is going to be retained by the bromine due to that vast difference in electronegativity. So the result is a carbocation intermediate that looks like this. And remember, anytime you form a carbocation intermediate, you are always susceptible to rearrangements. And remember, I put that carbocation on the secondary position because we're following Markovnikovs Rule. So you can see that we are going to break this carbon-carbon bond over here and form a ring expansion, because we can do that. So the resulting structure would look something like this, okay? And then remember, you can do a subsequent hydride shift to make that a tertiary carbocation. Okay, so from that tertiary carbocation, remember we generated a source of bromide. So that bromide now is a nucleophile, and that bromide can come in and attack that carbocation. So the resulting structure would look something like this. And there is no stereochemistry considered because the left and right side of the rings are equivalent. Okay, so the overall mechanism for hydrohalogenation of alkenes follows Markovnikovs rule, forms a carbocation intermediate, and is therefore susceptible to rearrangement. So I'll just write M for Markovnikovs rule, and I'll write carbocation over here, and then that means rearrangements. Okay, so those are the three mechanistic points, or key mechanistic points here. We're following Markovnikovs rule, we form a carbocation intermediate, and there is possible rearrangements. So when we suscept a alkene to a hydrogen halide, we should expect an alkyl halide product. So alkyl halide. Okay, so for the next reaction, we have acid-catalyzed hydration. So we have two reactants. We have acid and water. Acid acts as a catalyst, so it's going to be regenerated in the product, which we'll see in the mechanism. But, we're not really truly reacting with just acid or just water. So really the first thing is there's an equilibrium between water plus sulfuric acid is going to generate hydronium and the deprotonated version of sulfuric acid, which is this. Okay, so you can rationalize that our main reagent is going to be hydronium because sulfuric acid and water are going to mix together. Remember, sulfuric acid is a very strong acid, so it's going to protonate that water that acts as a base, and our main reagent is hydronium. So in terms of mechanism, so let's just draw hydronium out over here. So the first step in the mechanism is the pi bond grabbing a hydrogen because of that how electron deficient is. Remember, there is a significant dipole in the direction of that oxygen, making these protons positive. Also, that formal charge doesn't help, so that's why that hydrogen really wants to come off. So we're going to grab a proton from that pi bond, and then that oxygen is going to retain that electron density, forming water. So the result of that step would be the synthesis of a carbocation intermediate. So we're going to generate a secondary carbocation. So this, again, follows Markovnikovs rule, and we're going through a carbocation intermediate. So once we form that secondary carbocation, you always have to think to yourself, are there any other rearrangements possible to make it more stable? Well, yeah, there's a hydrogen right here that I can move over to get a tertiary carbocation. Okay, and are there any more rearrangements possible? So tertiary is pretty good, but we actually have a better one. So if we were to, move this hydrogen over, do another hydride shift, we actually synthesize a secondary benzylic. And even though it's secondary, anything that resonates would be better than the I guess, plain alkyl counterpart. So a secondary with resonance would definitely be better than just a plain secondary. And likewise, a secondary with resonance is definitely better than just a plain tertiary. And the reason that is a molecule that can resonate, so a secondary allylic, can delocalize that positive charge over a greater region. And, for tertiaries, we really just have slight stability or slight stability from those adjacent alkyl groups. So you can think of hyperconjugation as a slightly stabilizing feature, where resonance is a complete stabilizing feature. Okay, so the results of that would be something that looks like this. Okay, so now that we did that, we resulted with just water. Okay, and now water is our nucleophile that can come in and attack that electron deficient center. Okay, so we have that mechanistic step. And the result of that would be something that looks like this. Okay, so notice how we still have that protonated water molecule here. So we want to fix that positive charge. So what we can do is we can generate, we always assume that there's excess reagent in solution. So we can take another equivalent of water, and then that water molecule can remove a proton, effectively synthesizing an alcohol. Okay, so remember, we generated hydronium from this step, and hydronium can react with that deprotonated sulfuric acid to regenerate sulfuric acid or your catalyst. And remember, the definition of a catalyst is a reagent that is not used up in a reaction. It's present in both the reactants and the products, but it just makes the reaction go faster. So, once we did this reaction, we have to consider any stereochemical consequences. So we actually generated a chiral center here. So we would expect 2 enantiomers possible from attack of that carbocation. Remember that carbocation is an unhybridized p orbital present. So you can either attack from the front face of that orbital or the back face of that orbital, and that's what's going to result in a racemic mixture of products. So the 2 major stereoisomers of that would be a wedge configuration hydroxyl and a dash configuration hydroxyl. Okay, so let's just look at that bigger picture. So you saw that the first step was, the reaction between water and sulfuric acid, which generated hydronium. And then that pi bond, which was nucleophilic, was going to grab that partially electron deficient hydrogen and form a secondary carbocation. But that secondary carbocation went through 2 subsequent hydride rearrangements because each rearrangement was more and more stable. Okay, so we went from a secondary to a tertiary to a secondary allylic. Okay. Finally, once I form that more stable carbocation, that water nucleophile can come in and attack, but that attack can happen from either the front face or the back face of that orbital. So that means that we can have a racemic mixture possible. So the last step was finally just a deprotonation step to synthesize that alcohol. Okay? So, with acid-catalyzed hydration, you can expect that you're going to synthesize alcohol products. Okay, so for number three is the exact same mechanism for reaction 2. But I'm not going to go through all those steps because they follow the exact same thing. All we are varying is instead of water, we are going to use ethanol, okay, or any other alcohol species. So you can rationalize that acid as a catalyst is going to form the protonated version of that alcohol. So this structure, okay? So, that pi bond is going to grab that proton, and the result is a tertiary carbocation. So I'm sure you can see that over here. Are there any rearrangements possible from, making a more stable tertiary, from making a carbocation that is more stable than that tertiary position? And there really aren't. There's no subsequent hydride shifts that are going to make that a more stable position. So we're pretty good there. So now we can just take excess ethanol, comes in and attacks, and you can rationalize excess reagent in solution is going to come in and synthesize an ether. Okay, and again, let's think about stereochemical consequences here. So even though I went through that unhybridized p orbital carbocation intermediate, racemization is not possible here because we do not have a chiral center. That is not possible. Okay, so this is our structure. So by changing the reagent from water to an alcohol, we synthesize ethers instead of alcohols. And that should make sense because for the water, we're adding OH fragments. For this one, we're adding OR fragments. So that makes sense. All right, so I hope those first three reactions make sense. All of them followed Markovnikovs rule, and all of them went through carbocation rearrangement. So Markovnikovs and carbocation rearrangement. Okay, so halogenation. So this is the first new type of reaction we're going to see. So halogenation is pretty interesting in terms of its mechanism. The first step of the mechanism is a concerted step, meaning that all of the arrows happen at once. So if I were to draw chlorine out in its diatomic form, I can rationalize that that pi bond is going to come in and grab that chlorine, and that's going to force this chlorine to come off. But, in doing so, we really formed, a carbocation here. So it doesn't make sense for us to just form one chlorine bond. It makes sense for that first chlorine to come back and form a bridge. So really, the three arrows for the first step are a single-step concerted mechanism, and the result is a chlorine-halogen bridge. So the resulting structure is going to look like this. Okay, so that's the planar depiction of this, but I want to draw the real, stereochemical depiction of this structure, okay? So what I'm going to do is I'm going to take the starting material and I'm going to rotate it 90 degrees so that it's all horizontal. And in doing so, it's going to look something like this. pH stands for benzene. That's the isopropyl. So that is really the horizontal depiction of this. So you can rationalize that chlorine can either approach from the top face or chlorine can approach from the bottom face. So let's just call that A, and let's call that B. So the result of chlorine coming from the top face would be something that looks like this. And the result of chlorine coming from the bottom face would look something like this. Okay, so in doing so, we see that we have two different, major stereoisomers of this, but we're not done yet. So this is the main chlorine-halogen bridge. But remember, we generated a source of chloride anion, from step one, from that concerted mechanism. So chlorine is going to come and attack the more substituted position. And the reason that it attacks the more substituted position is because of resonance. So let's just take this first molecule, and if I were to draw resonance arrows, the resulting structure would be something that looks like this. Okay, so that's an isopropyl group. So you formed a tertiary carbocation, and if I were to resonate the other way, so if I were to do, let's change colors, so let's just do blue, the result of that would be something that looks like this. Okay. Well, I'm sorry, I dropped the pH. pH and pH and pH and pH. Okay, so you can see that we go from a tertiary carbocation to a secondary carbocation. So it makes sense for the nucleophile to attack the more stable carbocation or the more substituted position. Okay, so we can rationalize that chloride is going to come in and attack at that carbon, which is going to break the octet, exceed the octet at that position at that carbon, so we have to break that carbon-chlorine bond over there. So the result is a structure that looks like this. And if I were to do the same thing over here, we're going to attack here and open that. So the result is going to be something that looks like this. Oops, excuse me. Okay, so these are the two main stereoisomers of halogenation of alkanes. And it's important to note that these chlorines are 180 degrees apart from each other. So that is consistent with something called anti-addition. So because part of this, bridge, the top face of this bridge was sterically hindered, we could only attack from the bottom face. So we could only attack, from here, and we could only attack from here. And in doing so, that causes these chlorines to be on an anti-configuration. So remember that halogenation is stereospecific in the sense that, so there's no Markovnikovs rule to follow here because we're not forming carbocation. So Markovnikov and carbocation are not applicable. But you can rationalize that we have anti-addition because it's stereospecific. So anti, and I'll just write stereospecific. Okay, So that is the halogenation mechanism, okay? So definitely keep in mind that you can approach from the top face to the bottom face of that pi bond to form that chlorine bridge, and you want to attack the more substituted position because we showed those alternate resonance structures, and that nucleophile is going to want to attack, the more substituted position. All right, so let's move on to halohydrin synthesis. So halohydrin synthesis follows the exact same mechanism as above, but now we're going to have water come into play. Okay, so recall we're going to have that first single-step concerted mechanism. So I can just draw chlorine over here, and our mechanistic arrows would be pi bond grabbing a chlorine, and then that's going to cause that chlorine to break. But that chlorine is going to come back and form a bridge. So we can rationalize that our two main, intermediates are going to be something that looks like this, and something that looks like this. Okay? So in doing so, we generated a source of chloride, but what does that water do? Well, water is definitely more nucleophilic than chlorine because chlorine is completely stable in its octet configuration, but water would like to add in. Okay, so oxygen nucleophiles are definitely better than just a single halide anion. So we're going to follow that same rule that water is going to attack the more substituted position. Oops, so let me just change color. And that breaks the octet over there. And then water is going to come in here and attack that. So again, we're restricted to the opposite face of that chlorine bridge because of the lack of steric hindrance, you could say. So the resulting products for these two steps would be something that looks like this. Okay, so we would get something that looks like this. So, the last step would just be a subsequent depronation step. So you can show that water, another equivalent of water, is going to come in and just depronate those hydrogens. Again, you can draw water over here. It's going to depronate that hydrogen to form a functional group called a halohydrin. Okay, so, our two structures, I'm just going to draw one of them because here's that one. And you can say plus the enantiomer, so plus enantiomer. Okay, so it's called a halohydrin because we have a halogen close to a hydro group. So, and halohydrins are functional groups that are just separated by adjacent carbons. And you should note that this is also stereospecific and that we had anti-addition. And anti-addition results because of that bridged intermediate. So this is also not going to follow Markovnikovs rule. There's no carbocation intermediates, but we are going to follow anti-addition. And we are stereospecific. Okay, so those are the first 5 reactions. I hope that makes sense. Let's move on to the other reactions. So oxymercuration. So although the full mechanism isn't covered, there are some key mechanistic points with oxymercuration. So there are 2 distinct steps here. So we have a mercuric acetate, THF, and water, and step 2 is going to be sodium borohydride. So what do all those reagents do? Well, mercuric acetate looks like this. And what happens is, again, it's a single-step concerted mechanism that's going to form a cyclic mercuric acetate bridge. So this pi bond is going to, attack that mercury, okay? And that's going to result in the removal of one of these aceto groups, and then it's going to come back in and form a bridge. So the resulting structure would look something like this, and I'll keep it in plain. So we have Hg, OAC plus, and over here we'll just keep that isoterpial group, excuse me. Okay, so that's the cyclic mercuric acetate intermediate, and recall that bridge can either form on a wedge orientation or it could have formed on a dash orientation, but it's not going to be important yet. Okay, so we have that in step 1. Step 2, as well in step 1, we also have a molecule of water. And what water can do is, just like we saw in halohydrin synthesis, is it's going to attack the more substituted position of that mercuric acetate bridge. So we're expecting something that looks like that. Okay, so we are going to get something that looks like this. So we have an HGOAC over here, HGOAC over here, and we just had water come in and attack over here. Okay, so again, like we've always seen, that water molecule is going to come in and going to deprotonate that substituent to form a stable alcohol. So the resulting structure from step 1, this is the product of step 1, is going to be a substituent where there's HGOAC on the less substituted side, and there's going to be an alcohol on the more substituted side. So that is the product of step 1, and that is all you are expected to know in terms of mechanism for oxymercuration. But for step 2, just rationalize that sodium borohydride is a reducing agent, is a source of hydride, and that's going to basically erase this mercuric aceto, substituent and replace it with a hydrogen. So basically just removes that whole group. Okay, so then, that's our product, but we have to consider any major stereoisomers or stereochemical consequences. So we didn't form a new chiral center because the left and the right side of the ring are the same. However, we formed a different type of stereoisomer, and that's a geometric isomer. So remember, in cyclic structures, and more specifically like di-substituted cyclic structures, we can form geometric isomers, the cis and trans isomer. So we would expect, the tert butyl is going to stay on the same wedge configuration, but we could have the hydroxyl, a cis to that tert butyl group, and we can also have that hydroxyl group trans to that tert butyl group. So stereoisomers doesn't just mean chiral molecules like enantiomer and diastereomers. It can also reflect geometric isomers like the cis and trans isomers we see in these cyclic structures. So in terms of mechanism, definitely know about that mercuric acetate bridge. Understand the logic between why a water molecule is going to attack the more substituted position, and definitely rationalize why sodium borohydride is going to replace that mercuric aceto substituent and replace it with a hydrogen. Okay. So this reaction should be noted for not following, it is following Markovnikovs Rule by forming a more stable, forming an alcohol in the more substituted position, but we are not going through a carbocation, so no carbocation here. So rearrangements are not possible. So, a limitation to acid-catalyzed hydration, a limit to oxymercuration would be that there are no rearrangements possible, but in acid-catalyzed hydration with alcohols, we see that we can have rearrangements possible, so a more stable product. Okay, so that is reaction 6. So reaction 7 is hydroboration oxidation. So this is going to be an anti-Markovnikovs rule. So I'll just write AM for anti-Markovnikovs rule, and there are no carbocations here, so no carbocations. So what is hydroboration and how does it work mechanistically? So borane, BH3, was selectively chosen by organic chemists because the BH2 fragment of borane is going to sterically align for the less substituted position, and the other H fragment of borane is going to line on the more substituted position. And in doing so, we're going to see what that does in terms of addition of that alcohol. So the first thing I want to do is kind of draw a transition state. So remember, those are things where partial bonds are depicted as dashes. So, we can draw that same main sigma bond framework, but we can draw dashes here because we know that pi bond's going to break. And let's just draw the borane fragment. So that's BH, and we're going to draw the H over here. And there's a reason why I drew the BH2 portion, so that's this portion, towards the left, because it's less sterically hindered and it can align in that fashion, where this single hydrogen atom over here can align with the tert butyl group because it's more bulky and that hydrogen atom is a lot smaller, okay? So in terms of depicting the transition state, we know that the BH2 fragment is going to add to the less substituted side. That boron-hydrogen bond is going to break, and that hydrogen is going to add to the more substituted side. So it's actually syn addition over here, where the BH2 fragment and the H fragment add on the same phase. So this is definitely our transition state, so definitely be able to draw that on the test, but then the result of that step is going to be something that looks like this. Okay, and recall there is no really stereochem to consider because of the primary carbon over here. But we could just rationalize that if this were to approach on a wedge, that would also approach on a wedge, and if they were both to approach on a dash, they would both approach on dashes. Okay, so that is the product of step 1. So all that you don't know the mechanism for step 2, but you can rationalize that sodium hydroxide is a source of OH, and it's going to replace the BH2 group with an alcohol. So you can see we have the anti-Markovnikov addition of an alcohol. So recall in oxymercuration and acid-catalyzed hydration, we had alcohols add to the more substituted side. But in hydroboration, we have this key reactant, borane, that's going to cause us to add alcohols to the less substituted side. Okay? Those are the key mechanistic points here. So finally, 8, 9, and 10 are pretty quick. We don't really know their full mechanisms either. So for syn-diol synthesis, we have this weird reagent called osmium tetroxide, and the Lewis structure for osmium tetroxide looks like this. Okay, so the mechanism is a single-step concerted mechanism in terms of forming the first intermediate. So we can rationalize that what's going to happen is that pi bond is going to come and attack that oxygen, and then that oxygen is going to move over here onto that osmium, and then that pi bond is going to come back and swivel over and attack the rest of the pi bond. So, we have this single-step concerted mechanism, and this is also going to follow, I guess, that bridged intermediate where it could be either on that wedge or dash configuration. So I'll draw both intermediates, so it would look something like this. And I'm considering stereochemistry here. And you could also rationalize that you would get so that is, the first, I guess, product from, the first intermediate from osmium tetroxide. And we don't really need to know what water and hydrogen peroxide does, but water is going to do hydrolysis, which cleaves these bonds over here, and hydrogen peroxide is just going to regenerate the catalyst. So when we cleave, we can say that we are going to add, OHs in those places. So we are really expecting products that look like this. So, this reaction is also stereospecific in the sense that we are having syn addition of those alcohol substituents. This is the syn-diol synthesis, okay? And that's pretty much it for osmium tetroxide reaction, or the syn-diol synthesis, okay? So 9, ozonolysis, this is my favorite reaction. I think it's pretty cool. It's the only reaction we know so far that actually cleaves carbon-carbon double bonds. So it cleaves carbon-carbon double bonds, and in the place of those double bonds puts aldehydes and or ketones, okay? So the two reagents are ozone, O3, and dimethyl sulfide, so sometimes you might see that as DMS, okay? So what happens is that pi bond is going to cleave. So let's number this ring. So 1, 2, 3, 4, 5, 6, 7, 8. So let's draw an 8-membered chain, sorry. 1, 2, 3, 4, 5, 6, 7, 8. So on carbon 1, we didn't touch that aldehyde, so we can keep it. On carbon 2, we cleaved that double bond, so we should expect a carbonyl to be placed in that position. Carbon 3, we already had a ketone. 4, nothing. 5, nothing. 6, nothing. 7, we did cleave at that position. So 1, 2, 3, 4. So let me number this 1, 2, 3, 4, 5, 6, 7. And remember, 8 was just that methyl substituent. So this would be the opened chain format once we subject that ring to ozone, okay? So it's pretty obvious. All you have to do is rationalize that at carbon 2 and carbon 7 was where we broke those carbon-carbon bonds, carbon-carbon double bonds, and we're going to put ketones or carbonyls in that place, and they could end up being either a ketone or an aldehyde, okay? The mechanism we do not cover. Okay, catalytic reduction is the last reaction. Finally, we're here. And this is going to be syn addition of hydrogen to a double bond. And this is done in the presence of a metal catalyst. It could be platinum, palladium, or nickel. Okay? And what happens is you can imagine that hydrogen is going to add in a syn-type fashion on both sides of that carbon-carbon bond. So it could add on a dash configuration, or it could add on the wedge configuration. So let's just say wedge and wedge. So in doing so, that's going to reduce that pi bond into, an alkane, and that might have some stereochemical consequences on those substituents. So if I'm adding, a hydrogen on a dash, that's going to force that methyl group onto a wedge. So we would expect this major diastereomer. And then really the main stereoisomer of this project, if the hydrogen were added on a wedge, would be, this methyl group, this ethyl group, excuse me, on a dash, and then we're going to keep that methyl group on a wedge because we're not doing any chemistry there. So we have two main diastereomers from this. That's why I say you can use that shortcut saying plus racemic or plus enantiomer on your test, but be careful because sometimes they're not enantiomers, they're going to be diastereomers, so be careful. Okay, so let's just go over this roadmap on the bottom. So this is going to sum up all of our reactions together. So for A, we clearly see that we're taking this pi bond and we're suscepting it to bromine and water, so we're thinking halohydrogen synthesis. So we're expecting a bromine bridge intermediate and water to attack the more substituted position. So if you thought this product excuse me, and we are going to have, okay, so you can clearly see that the hydroxyl group added to the more substituted position, which was the methyl substituent, and the bromine's over there. So remember, we generated 2 chiral centers here, so you would expect 4 products, but you don't get 4 products. And the reason you don't get 4 products is because the bromine bridge is, either, I'm just going to draw a brief, quick structure, either on a wedge or a dash. So that limits us to attack from either the front face or the back face. So we're clearly going to get, anti-addition of this bromine and this hydroxyl group. But the hydroxyl group can only add onto the less substituted side. So, the more substituted side, rather. So we can rationalize that water is going to come in and attack here. So the major stereoisomers of this are only going to be this one, and you can also get this one. So if this was the bromine on a dash, we could only have attacked from the front face, and those would be my 2 major stereoisomers. So be careful. It looks like you can generate 4 major stereoisomers, but only 2 are possible. Okay, so for B, we're substituting this alkene to, hydrogen and platinum, so we're thinking syn addition of those hydrogens, so either both on dashes or both on wedges. So in doing so, you would get 2 major stereoisomers where this methyl group is either on a wedge or this methyl group is either on a dash. Okay, that's B. For C, it looks like we open that ring, and in that place we put carbonyls. So if I were to, maybe number this, 1, 2, 3, 4, 5, 6, 7, and if I were to do 1, 2, 3, 4, 5, 6, 7, it looks like at position 2 and position 6 and position 2 and position, 2 and 7, I should say, over here, not that one. We added carbonyl. So the only reaction we know for opening carbon-carbon double bonds would be ozonolysis followed by dimethyl salt. So that's C. D, it looks like we are adding an alcohol, but we're adding that alcohol to the more substituted position. So there's actually 2 answers for D. So you could have said, H2O and some sort of acid catalyst, that's acid-catalyzed hydration, or you could have said oxymercuration. And in step 2, remember, it's just sodium borohydride. Okay. So you can use either one of those answers to get to that product. Okay, so for E, we're suscepting that alkene to a osmotic oxide reagent, so we're expecting syn-diol synthesis. So you would expect, those hydroxyls both coming on wedges. That forces this methyl on a dash. And you would also expect, both of those hydroxyls coming on dashes, forcing that, that methyl group on a wedge. Okay? And that sums up the Chapter 6 material. I hope that helped, and a Chapter 7 video will be coming shortly.